Here's a photograph of an apparatus I set up previously. I apologize, I didn't have it set up live here in the classroom for you. But you see what I've done is, you can tell it's the room that we're currently standing in. But I hung two balloons from the ceiling and invite students to look at those balloons. And I notice a curious thing, a nature of the universe that I would like to describe and explain. And it's that these two balloons here, which I would expect to hang directly below the mount points, you can see I've added a dark line here to indicate where the string is. I would expect the string to hang vertically. As a matter of fact, according to Newton's second law, that's what should happen. The force of gravity directed downward, the force in the spring directed upward, and force equilibrium so that the acceleration is zero. That's the language we've spent most of our time together investigating. And yet what I notice is that the two balloons actually are drawn toward each other such that the strings that support them are drawn from the vertical. Now, I understand Newton's laws. I can explain this easily. In order for this to be true, when I draw a free body diagram showing all of the forces that act, I want those forces, or I expect those forces, to act in equilibrium so that the net force is equal to zero, which means there must be an unseen force F that acts on the left balloon and an unseen force F that acts on the right balloon. Not only that, according to Newton's third law, these two forces should be action-reaction forces. They should be equal in magnitude as they're opposite in direction and should have the same nature. So if I stumble upon this phenomenon, I just observe it happening in the universe, and I have an innate human curiosity, then I say, well, how can I explain that? Why should it be so that these two things would pull toward each other like that? And someone who's studied a lot of physics, and as it happens, a bit more physics than we have necessarily in this course, might look at it and say, I know, just as the moon is attracted to the Earth by the unseen force of gravity, and indeed the Earth is attracted to the sun by the unseen force of gravity, I imagine that these two balloons are attracted to each other by the gravitational force. And that's a sensible thing to say, because when you encounter a new phenomenon, the first thing that you're going to do is try to describe it in the context of things that you know. In this case, universal gravitation. The trouble is, I can take the balloons and measure their masses and measure all the angles and make all of these measurements, and when I begin to do the arithmetic and try to account for what I observe in the context of gravity, I find out that it fails. Not only does it fail, but it does so spectacularly. Because I would discover in all of my calculations and machinations that the force that is pulling the two balloons together is 10 to the 40 power stronger than gravity. Now, it's a big number of strength. What? You mean they smash together? No, of course, the balloons have a very small mass, and so the gravitational force is extremely small. We don't experience gravitational forces in our everyday lives. We do not, as attracted as we might be to other people, that attraction is not gravitational. You don't feel the pull of objects around you in your everyday life, because gravity is a very, very weak force. And so 10 to the 40 stronger than gravity is still not a tremendous force, but it causes the balloons to move toward each other. It is a force a trillion times larger than gravity. And it's a force that, if you think of it in the context of our course of study, we have never encountered before. It's a new kind of force. It's true that I can use Newton's second law to figure out the things that happen in my universe in the context of the forces that I know. Normal forces, spring forces, pushes, pulls, rocket motors, buoyant force, whatever. And I can work all that out. But I can also use Newton's second law to discover forces that I've never encountered before. When a system, like these two balloons, does something I've never seen before, well, then I have to open the book to a fresh page and realize that I've discovered a new force. The force that I'm alluding to here, obviously, is the electrical force, a new kind of force of nature that we're going to spend quite a bit of time investigating, not only in its sort of the nature of the universe sort of context, but also as a practical matter, because it turns out that this effect we use in our day-to-day lives as a key aspect of our very, very advanced human technology. But the start of all of this goes back to ancient Greece. Now, in terms of ancient Greece, there's a great deal of philosophy, but not a great deal of science. As you learn in Western civilization, science didn't really get going, a full head of steam until the Renaissance. But there was a lot of industrial craft in Greek times. And there was a substance that the ancient Greeks were very, very interested in, and that was sort of fossilized pine sap. A substance called amber. The sap leaks out of the tree, it piles up on the ground, solidifies, and then over a long aging process becomes almost like stone. Here is a picture of amber, and I hope that you look at it and you go, oh, that's pretty, because that's exactly what the Greeks thought. Also, by the way, you can see that there's an insect trapped in this amber. When the amber was in its fluid form, the insect was attracted to its chemical properties, landed on it, became stuck, and then was forever entombed inside, Jurassic Park style. But the amber is quite pretty. And so craftspeople in ancient Greece would take the amber and fashion jewelry from it. Not do science with it, but fashion jewelry with it. Here I have a plastic rod. I won't mind at all if you imagine that it is a rod made of amber. I don't have one of those, but I do have this plastic rod. And if I'm an ancient Greek and I'm fashioning a piece of jewelry, I find that the amber is most spectacular when I polish it. So I have a piece of felt here, and felt is typically, this felt, I do not know its origin. It is probably made from artificial fibers. But felt is typically made from animal fur. So I would have some animal fur in my piece of amber, and I would be polishing it for the purpose of making an attractive piece of jewelry. While I'm in the process of doing that, it's not a scientific investigation, but while I'm in the process of doing it, I would likely discover some strange effects. Effects that you sometimes encounter in your everyday life. Pardon me. You see that I have this can here, and I'm not using a full-size soda can because I want the mass to be very small, because I'm observing a very small effect. Imagine that you're a Greek and you know very little about the scientific laws of nature. This would appear like magic without touching the can at all. It moves under the influence of the rod according to some unseen nature. That's pretty spectacular. Okay, let me do it again. All right. So I place the can here on its side. It does not work unless I polish the amber, and without touching it, I can make it move. Sure. This phenomenon is not dissimilar, smaller effect. This phenomenon is not dissimilar to when you're at home and you're comfortable, you put on your flannel pajamas and those slippers that look like little bunny rabbits, you know the ones, and you shuffle around the house and then you reach for a doorknob, you get shocked. The Greeks were able to observe all of these very, very curious natural effects, but without a scientific method and a reason of investigation. It was just that, a mystery that would not be understood. In fact, it's so mysterious that it was not understood until way after Isaac Newton's time. This aspect of the universe is really difficult to get at. At any rate, a fun fact for today that I enjoy very much is that the ancient Greek word for amber is electron, which is where that term comes from. Whenever I'm talking about the history of electricity and its partner magnetism, I always run up against the fact that students already know you're part of a modern civilization, you have a level of sophistication, and you know things that every school child knows. And it kind of spoils the history a little bit. But the reason why we have the word, or use the word electricity, and because we know the modern term electron from our studies of chemistry, that's the origin of the word. It comes from the ancient Greek observation of this, and it wasn't until the very late 1800s that the human race finally got its arms around it and began to understand what this electrical effect truly was. Here's a familiar statement that I hope you have completely internalized. Mass is the measure of an object's inertia. Inertia is a property of matter. It's one that's way more obvious than the electrical effect. I pick up an object and I shake it around and I find that it resists acceleration. I get a quote unquote heavier object and I shake it around, and I find that it has that property to a greater extent, where the property is resistance to acceleration. Mass is the measure of an object's inertia. The larger the mass, the larger the effect. By the effect, I mean resistance to acceleration. We're going to do exactly the same thing for our investigation of the electrical effect. We will assign to physical objects a property that you can measure, that describes the extent to which it has within it that effect. Charge is the name for the property that matter has that describes that effect. Charge is the measure of an object's electrification. By electrification, I mean the extent to which it has the electrical effect. Charge is the measure of an object's electrification. The larger the charge, the larger the effect. And here in my demonstration, I rubbed this plastic rod vigorously, and I got a large effect. But then I was asked to negate the effect so we could see a neutral result and hold it over there and see no effect, because there's an extent to which the apparatus has the effect. And we call that charge. It's not an incredibly useful thing for calculating to think of mass and charge in the same way, but to me, from my personal point of view on this issue, mass and charge are similar to the extent that they are a number that describes the amount of an effect that I observe. The thing is, mass is way more everyday for me. I put a thing on a pan balance, and the mass is associated with the weight of a thing too, so I've got that. I put a thing on a pan balance, and I know, well, this one's going to have a large mass, and this is going to have a small mass. Electric charge is more difficult to make tangible because you cannot see it. If I give the plastic rod a large charge, it looks, weighs, smells, tastes identically the same as a rod with a lesser charge. That's going to be a little bit of a struggle going forward. It means I have to work harder as a teacher and you have to work harder as a student, because the electrical effect is completely invisible. Sure, I can make the can roll across the lab table. That's a visible effect. But I never see the cause underlying it because it is outside of human experience. That's why I use the term intangible, can't be touched. Zipping ahead in human history, a little bit of local pride for us here. Ben Franklin famously studied the electrical effect. I think you all probably as little kids were exposed to an idea that Ben Franklin flew a kite with a key tied to it in order to attract lightning, which he certainly did. But just like Newton sitting under a tree and getting hit by an apple, that story is a bit apocryphal. Along with the zillion other things that Ben Franklin accomplished, being a founding father of the United States, everything he did with post offices and fire departments and printing presses and all of that things that he did, he also was an enthusiastic scientist. And he studied the electrical effect, which was all the rage in his day, and he concluded from his own observation that there must be two kinds of electricity, meaning that there must be two kinds of electric charge, which is really a revelation because there are only two kinds of mass. At the time that Ben Franklin came to the scene and began studying these things, I seem to have lost track of my black rod, if anyone sees it. I've set it down somewhere. Oh, underneath the paper. Oh. Imagine that this rod, which is in fact plastic, is a rod of amber. Amber is one of a classification of materials called a resin. And so when I create this electrical effect by rubbing the rod with the fur, I get a kind of electricity that in Ben Franklin's time was referred to as resinous electricity. Resinous electricity. Here I have a glass rod and a piece of silk. It was also observed in Ben Franklin's time that if I rub a glass rod on a piece of silk, I also get electrical effects. But the electrical effects are curiously the opposite. If I were to take the resinous rod, the amber rod, charge it up, I might be able to attract a thing, and that is very mysterious. But if I do the same thing with the glass rod and I rub it with silk, the glass rod will repel the thing. One attracts, the other repels, leading Ben Franklin to the conclusion that there are two kinds of electricity. The kind of electricity when you rub a glass rod with silk is called vitreous electricity. And the rod is called resonance electricity. Now, if you've never heard those terms before, I wouldn't be surprised because they are archaic terms. We don't call them that anymore because Ben Franklin made a choice. Instead of referring to the different kinds of electricity as vitreous and resonance, he called them positive and negative. Positive and negative in the mathematical sense, like numbers that you calculate. Because by the time Ben Franklin started investigating this, human science had advanced to the point where we began to realize quite clearly that the universe is based on mathematical laws. And the expectation that there were mathematical laws on the way, Ben Franklin decided to give the sense of electric effect mathematical names. His expectation was that there would be equations that would have plus or minus signs in them depending on the type of electricity that was involved. And he was completely right about that. Ben Franklin was a huge fan. Remember, we're talking about the 1700s. Ben Franklin was a huge fan of Isaac Newton, as were all thinkers of the time. Appreciate that to Ben Franklin, Isaac Newton is a celebrity. And Isaac Newton had written about his idea that the universe was based on mathematics. Quite famously, Isaac Newton said, numero pondere et mensura deus omnia condit. But since we don't speak Latin, he said, of number, weight, and measure, God created the universe. Isaac Newton realized that the universe was governed by mathematical laws. And it was all the rage. But he knew there would be measurements, and he knew that there would be math, and so he prepared us in advance for that eventuality. So there are two kinds of electricity, and this is the way the logic of it works out. Imagine that I have an object A here, and I prepare it by rubbing it with the appropriate materials. I prepare it in such a way that it attracts object B. And I've added arrows to my diagram here, suggesting that they attract one another. And then I also prepare a third object, C, which is also attracted to B. So A attracts B, and B attracts C. What you then immediately discover is that when you bring A and C in vicinity of each other, they repel. This is the logic of electricity. It can be repulsive or attractive depending on how the charged objects are prepared. Well, they can either be an amber rod or a glass rod, and that's how they go. The electric effect can either be resonance or vitreous. Ben Franklin clears this up for us by calling them positive and negative. And what we realize from this logic is that objects with opposite charges will attract each other. Just as in my balloon experiment, the reason why my two balloons attract each other is because one has a positive charge and the other has a negative charge. And so they exert an attractive force. If I have two positive charges in the vicinity of each other, as I see here in the leftmost diagram, those charges repel each other. You could say the inverse, that like charges repel. Whether they're positive and positive or negative and negative, they repel in both of these situations, as we can see from their deflection from the otherwise vertical. It's opposite charges that attract. It has been said sociologically that in issues of romance between human beings, it seems to be that opposites attract one another. It's not true. It's just a human saying for a bit of fun. But it's a way that you could remember it. Opposites attract. And if opposites attract, and the only other option is repulsion, then it must be true that likes repel. I already mentioned that as students in our modern society, you already have an inkling of where this comes from, because you know that matter is composed of atoms. Ben Franklin was aware of this notion that material substances would be composed of a finite element, that it was the atom of its existence. He was aware of that philosophical idea, but for Ben Franklin, it was not a scientific reality. And for you, it is. It doesn't trouble you much when I show you a helium atom. This picture of a helium atom bothers the bejesus out of me, whereas you are very comfortable looking at atoms as if they're like solar systems, like this. This is not really the true nature of atoms. The true nature of atoms is described by a branch of physics that we will not study called quantum mechanics. But this is good shorthand for the behavior of atoms. It's familiar because you can see that there's a compact region of charge at the center, what we call the nucleus of the atom, that has two positively charged particles that we call protons. To be pro something is to be for it, and to be for it is to be positive, thumbs up. Protons, positively charged particles. There are two protons in the nucleus of helium, as shown here, and there are two electrons in orbit. They have opposite charges, which means they attract, which is the reason why atoms exist. The material substance of the universe in the context of the periodic table is created because of the electrical effect. Atoms don't exist without electrical attraction, binding the negatively charged particles to the positively charged nucleus. But that's not my interest today. I have a negatively charged electron attracted to positively charged protons. And according to Newton's third law, by the way, the proton's attracted to the electron. There's electric charge in this atom. But if I view it from far away, because atoms, as we know, are very, very small, if I view it from very far away, the negative charges of the electron and the positive charges of the protons are so close together that I cannot in any way observe their electrical effect. In a sense, you could say the positive charges cancel out the negative charges, that all of that positiveness of the nucleus minus all of that negativeness of the electron adds up to zero. And it does. Atoms are electrically neutral because typically, and you know, of course, from your study of chemistry, that an atom can be ionized by adding or removing electrons, and that affects the behavior of how they form compounds and all of that. Yes, is true. But in their natural state, atoms are neutral. They have as much of the positive electrical effect as they do the negative electrical effect, and as a result, they have no electrical effect. If you want to get electrical effects, even in chemistry, you're going to have to remove some electrons or add some electrons. And that's exactly what happens when I rub a glass rod with a piece of silk. The glass rod has a molecular structure, molecules being combinations of atoms. When I run the silk, which has its own atoms, by the way, across the glass rod, it strips electrons off the atoms of the glass rod, scraping electrons off. Well, if the glass is originally neutral, having as much of the positive as the negative, when I remove the negative, I'm left with a net positive. The vitreous charge is positive charge. The glass rod becomes positively charged because electrons are removed from the rod. The rod is neutral when I take electrons away, and they're negative charge. The glass rod, you could say, is left with a deficit of electrons and is therefore positively charged. When I take the amber rod and rub it with fur, the opposite effect happens. The amber rod strips electrons off the fur. And whereas the amber was originally neutral, the excess of negatively charged electrons on the amber results in the amber being negatively charged. Resinous charge is negative charge. The glass rod has a positive charge because it lost electrons, and the amber has a negative charge due to the gain of electrons. When electrons are transferred from one object to the other by the action of friction, this is called the triboelectric effect. Fancy name for electrons being transferred by friction. This is called the triboelectric effect. Here's the thing. Atoms are made of electrons and protons. So why don't the protons move? Like, why has it got to be the electrons? There's a very simple answer to that. We always think about electrical effects in the context of the electrons moving around, because electrons are really, really, really low mass particles. The mass of a proton is 1,000 times greater than an electron. The mass of a proton is 1,000 times greater than an electron. So when they're subject to the same electrical force, action-reaction pairs, equal in magnitude, when they're subject to the same force, the acceleration of the electron is 1,000 times greater. It's the electrons that move. It's the electrons that move because they're light and wispy. The electrons do all the moving around. So as I seek explanations for everyday electrical effects, for example, how is it that I touch the doorknob? I've got my bunny slippers on, and I touch the doorknob and there's a spark. I've been walking around in my bunny slippers, accumulating electrons, probably dragging my feet, because it's a PLT day. Dragging my feet and scraping electrons off the carpeting. Those electrons are now on my body. I become electrically charged. I touch the doorknob and whammo, whammo. So as we continue the discussion and describe more and more electrical effects, I'll be talking in the context of it is the electrons to move, because when experiencing the same electrical force, electrons have 1,000 times greater acceleration than the protons. This is just the beginning of our understanding of the electrical effect.